Sorry, just
Hello,
before you continue.
it's fine.
Is it necessary to get, can you hear me?
Yeah, I can hear
Uh,
you.
is it necessary to get the textbook for this subject, or do you think we'll be able to manage without it?
I recommend getting it. Is it a problem for you to get the textbook or what's the problem?
No, no, I can get it in a week. I just want to know, like, if it's necessary or not.
Yeah, get it. I would recommend get it. It's good to have a hard copy of
Oh,
it because you'll be
so
using it for the semester for the semester and next semester. So yeah,
This
it's not
particular
that.
textbook.
Yeah, Trotsky. Yeah, that's correct. So I
yeah,
recommend
sir,
getting it.
because the book
Okay.
is 500 rand.
Yeah, that's all right. It's $500. You guys should be. You guys not financially stable yet.
For a working man, it's fine, but some of us.
No, I understand, man.
Oh, even
I
for those
recommend
that
getting it.
are working stuff.
Sorry, Mr. Silva.
Oh, no, it's fine. Continue.
Okay, great. Can I move on? So your audio and constant reconnecting. Let me just check, Megan. I think um can everyone else hear me quite clearly? I'm just checking. I don't know, maybe Megan's network is poor. I'm just not sure. Um am I clear to everyone else? Okay, so yes. Yes, Silas. Okay, great. Yes, you're raising your hand over there. Okay. I think Megan has a problem with the network. I wonder what's going on. Um, okay, let's proceed. Okay, so we continue off with the series arrangement. And what we're going to have to do now. So, what happens if you have a case where you've got a compound rod, however, it's loaded in various places at various parts of the thing, right? How do we tackle this problem? So in this case, we can't just uh, simply just find the use his loader. We got to now find the load for each section. Now this here, this technique we're using, it's essentially um, it's based on the principle superposition, and it's within your textbook, and it states there that if a linear relation exists between force and the effect it causes, the resulting effect on a body subjected to several forces equal to the algebraic sum of partial effects. Now, this is a simple thing we'll be doing in lecture, but idea is taking section by section by section by section, and in the end, we just add them all up, and then we get the overall effect of exactly what happened. So, let's do this problem. This should be example 2.2 in your textbook, page 31, and also a very common problem which you can expect. So let me just copy this guy quickly. Oh, that's not that one. This one over here. And there's a lot of questions like this within your textbook, and make sure you do all the exercises. That's only in your favor. Um, I have put some very old question papers on Blackboard, and I recommend you go over each and everything so that you competent for the subject. We can meet the outcomes. Okay, let's just quickly share the whiteboard, the blackboard, or whatever this is. Okay, and you see, yeah, so in a question like this, let me do the question first. So determine A, the magnitude the magnitude of force P. So P is over there, it's on your right. This guy, we'll zoom this. So that's P, you need to find. Oh. Okay. So check, okay. seems fine now. So we're going to find this load over here, P, this guy over here. Then once we have that, so required for equilibrium of the member. So of course we assume this in equilibrium, right? First condition of equilibrium, the forces. And then we're going to find the total change in length of each member. And this is a very common question. We've got a few of them within your book, which actually goes over. We've got a few of these, about 10 questions which discuss this type of question. Definitely one of the questions you might get. Right. So the first thing we do, we've got to find P, right? So the way we're going to do it, we have to sum up all the forces in the x direction. So first condition of equilibrium, second condition is of course of moments. So you can say sum of the forces in the x direction. I'm going to call it P, you can call it F, doesn't really matter. So we've got 20 plus 20, right? We've got negative 40. And of course, I'm assuming that positive is to the right, negatives to the left. So we always use our Cartesian plane over here. So, plus negative. Also got a z plane. Fine. Then we have plus 30. And then we have negative p, sorry, because p is going in the opposite direction, and that's all equal to 0. So we're just summing up all our forces. And if you add this up, you should get 20. This should be negative 10, I think. That's correct. No, that's 10, exactly 10. So that's 50. It's 10 kilonewtons. 10 minus P equals 0. Of course, we can say P equals 10. So P is 10 kilonewtons positive. So I think what it also means that P is not acting in, well, is P going to be 10? Although the magnitude of P is going to be 10. So you shouldn't worry about the positioning of it. So P now, we know that it's 10 now. P 10 kilonewtons. Next step, okay, the first step we did establish it as a series arrangement, right? So the first laws we're going to be applying, I should have mentioned obviously first the forces. Remember A, B, exactly the same force in B, C, see the same force in C, D. You don't have to write this down, but just worth writing down. And of course, the change in length, total change in length will be equal to the algebraic sum of these. So that's that, LBC, etc. You get the idea, right? Series arrangement. Okay, so how we take this? We do this section by section, right? Principal superposition. So let me say for element or part B, right? Element just means a sub piece or whatever. I just call it element, right? We have, take it over here. That's A and B. Now we have to sketch. So now we know on A side we've got 20 kilonewtons going this way. And on the other end, we've got 40 kilonewtons, right? Okay. And the reason why we're doing, we try to see which sense, whether it's tensile or compressive, what kind of force, what kind of sense of the force inducing this thing, right? Then we have to look at the next force, which is 30, and 30 is going that way. So we say 30 kilonewtons. Then we look at 10, and 10 is going to be going that way. No, so let me just make sure of this. Just to make sure what I'm saying here. Don't want to derail you guys. So we've got on B, we've got 40 going that way, we've got 30 going that way. I'm sorry. 40 going that way. Yeah, and P is going to be 10. Yeah, okay. So what we do, we just sum up the forces, and if you look at this side, we've got 40 minus 30, right? Oh, sorry, forgive me. the minus 40 plus 30 minus 10, that's minus 50 plus 30 will give you minus 20. So what it basically means, if you sum up the forces, you're going to have section AB is being compressed by 20 kilonewtons. Right? I hope you all got that. And we're going to be doing a similar thing for each section. So once we have this, we can work on our change in length now, right? So our change in length for element AB is going to be, there's a question there. I thought I would get a question. Is 10 not positive? It's going in the left direction. Do you see it? It's going in the left-hand side. The magnitude, like the value is 10, man. I made a mistake, but it's still going negative. So it's not, it's 10, but it's, the magnitude is 10, but not the direction of it. We just solved 10.
So doesn't it matter that it came out as positive?
No, it doesn't matter because it's actually 10. That's the idea,
So,
but it's still going in the negative direction.
So you're just getting like an absolute value when you follow the arrow on the diagram.
That's correct. Yeah, we're getting the absolute value in following that. That's what I mean. You'll see once you do more. That's
okay.
And also, how you know you're correct, Mr. Silver, is that you're expecting 20 on the one side and expecting 20 on the one side. Remember, this is equilibrium, so the forces must balance. So that's how you always know. For each section, you're gonna pick up a pattern like that.
Okay.
Okay. So we have AB, right? And then it's gonna be stress L over E. It's all made from the same material, right? This is correct. They're all steel. So the force for this section is 20. The length is 500 more. So I'm just doing free again. So it's power 4. The area is, what's the area of that? Is it 20 more? Times 200. So what's important to note of this is that AB, the force in AB, so I'll say FAB equals 20 kilonewtons compressive, I'm just going to call it comp. That means AB is decreasing in length. So when we're going to be adding up the total length, this will be negative, right? So you can have this minus 20, or I normally prefer to say, you can say 20 kilonewtons, brackets C, to show you the sense of what's happening here. The sense of negative and positive show direction. So let's get back here. Positive is this way. Negative is that way. For the X direction, obviously, right? We're not dealing with the Y direction. So anyway, so if you find the change in length of this, you should get a value of 159.15 meters. So what it means is that for this part, under that loading conditions, this is shrinking. So you can say a decrease. It decreases by that much, or that loading arrangement. Is that clear to everyone? Everyone get that for the first element, for the first part? Thank you, Brent. Anyone else? Everyone else? You'll pick up the pattern as you move along. Okay, thank you. So next, we go to, for the next element, the AB, and it's BC, right? So that's the guy over there. I think I should, just give me a second. Let me write under this. Where, so we are, element BC. We take our element there. So BC is going from here till there, which is 1 meter. It's normally It's normally all positioned for you now quite nicely. Right, so at B, we've got 40 going this way, and this side we've got 20. So see, there's a 40 and there's a 20. On the other end, we've got 30 going that way, and we've got 10 going that way. So if you sum all of these guys up, you're going to end up with, like I said, 40 minus 20. You've got 20 going that way in that direction, negative direction. You've got 30 minus 10, and you've got 20 going that direction. Can you see? So you're going to find the same magnitude, and normally it's always either going to be tensile or compressive, obviously. But this one, so what they're saying between part B and C, that this is suffering from a tensile force or tensile stress. So we can say force BC equals 20 kilonewtons, bracket, open bracket, close bracket, T. Do exactly the same thing here. So we said the change in length of BC is equal to 20. The length is going to be what? A full 1 meter. The area we can find as well. That's 30 more times your, what is it again? Your modulus E. So E, of course, is 200. I'm not going to write that. And once you find BC, you should get 141.47. And this is increasing length because it's positive, it's a tensile force, so increase. Okay, just check the chat there. Same force, different nature. Oh, I like the way you put it here. Same force, different nature. Yeah. Nature, the nature, yeah, you could say that definitely. So we're all happy with BC. Okay, so I want you guys to try, what's the next one? BC, CD now. Please zoom. Yes, Mr. Silver, my apologies. My apologies. See, if you had a textbook, it would have been better for you. Okay. Let's see. Hey, sorry about that. All right. You guys managed. So what's the force acting on CD? Before I move on. That is not correct. Are we all happy with this? Any questions? So all we have to do is basically find change length for each section. We could also find the stresses like we did before, just as the previous example, and different ways to assess this question or examine this question. Are we happy with this? Okay, so we're not happy. Michaela, Sibusiso, Sanazo. So any questions, guys, before I move on? Any questions? Mr. Silva, you still there? Okay, great. Super self-explanatory, arguably. All right. I'll just give it a minute. Then I'll move on to the next question. So we do our last question on series, and then we move on to parallel. Okay, so let's go on to the next question. Last series one for the day. Just going to prepare it quickly for you. So in this case, once again, we have a series arrangement, right? What's happening with it? We've got two steel rods basically attached to a copper rectangular bar. Now this is a very common question because normally a very tough question for series arrangement has the following elements. It has different sizes, so different sections, and it have different materials. So that makes it a bit more tricky. Nevertheless, let's see the question. Two steel rods AB, diameter 10, and CD, diameter 15, are connected to a rectangular cross section 15 by 20, right? Determine the stresses in AB, BC, and CD. If the total elongation subjected to a force P, which we do not know at the stage, is 1 mole. So what they're saying is that the total force is equal to the total change in length is equal to 1 mole. So we know this is a series type question, and then we have two conditions for series. Just get that here. So let's figure out why my thing is misbehaving here for some reason. Just have it there, lock it. The forces are all equal, so FAB equals FBC and FCD. Next condition, the change in length, total change in length is equal to LAB plus L, of course, delta. That's just delta LAB plus delta LBC plus delta LCD. Great. Okay. So what we're going to have to do now. Now, the first thing we need to do is we know that I'm gonna show you how I'm gonna kind of intuitively solve this question. We have the one unknown is the change in length, right? So we know the total change in length, right? Subjected to that load there, must give us 1 times 10 to negative 3. So whatever the load is, each part must kind of tally up algebraically. The algebraic sum must equal to all of that, right? So we know that this must be stress AB, and of course we know change in length is stress length over E. We know that the length is 0.6, and E is going to be 200 in this case. That's just steel rod, plus the change in length at BC, which is copper. So stress BC times the length of that is 0.8. Each copper is 100. So for instance, Mr. Silver, again for you, is that maybe I might say that the materials are some random materials, not random, but then you have to go find the properties off the table, if you know what I mean. And then it's also 200 here, and this is my stress BC for the length of 0.4. Sorry, that's stress CD. Forgive me. Do we all agree with this so far? You all know what I did so far. You guys maybe read the question again. Please, guys, please interact with me. We are here to learn. I'm not here to just talk. We're here to practice, concurrent to learning. The practice is now. You're studying while we are busy here. Okay. Fine. Now what we have to do, obviously, if you think about this, we're going to need somehow to these stresses, we need to somehow replace, right? We need to make one known here, right? We need to find one known variable here to solve this. But luckily for us, we have a force condition, right? The forces are equal. So I'm just going to say this is equation 1. You shouldn't really do that. Doesn't really matter. So we know that the force in A, B, and force in BC, right? So that's going to be, so you know that stress is force over area. Therefore, stress times area equals force. So this is what I'm doing over here. So stress AB times its area. So its area is going to be pi over 4. That's just pi over 4 times, that's what the diameter is, 10 mole, 0.1 or 0.01 squared. Stress in BC is, now that's a rectangular section, and that's going to be 0.015 times, it's given there, 0.02. But have just done this if you wanted. Want to be fancy like me, times 10 to the negative 3 times 20. Now what we do here, we're going to find a ratio, right? And then we're going to say stress AB equals stress BC. Of course, we can divide out these numbers, and you're going to end up finding that stress BC AB is going to be equal to 3,820. Do you guys agree with me there? Who sees that? So if you divide that out, you should get that. Oh, 197. Are we happy with this? So now, if we're going to use, for instance, so we can use BC as our chosen variable. Now we can substitute this guy into 1. We'll do it at a later stage. Right? So this is going to go this guy is going to go in there. So now we have to do the same, and we're going to have to say FCD equals, or FBC equals FCD. And can I get the ratio from you guys? What is the ratio for this? So remember, you got to find the areas, divide the areas out here. This would be equation 3. So what's the ratio? So remember here, BC has the same area again, which is going to be you guys are following? So what's my ratio for this guy? And number 3. Anyone, what's the ratio? Right. So guess no one is everyone still following what I'm doing over here before I proceed? So what you're going to get is stress BC equals 0.589, right? And of course, we want CD in terms of BC, not this way. So we just have to divide on this side, and then we're going to find out that CD is equal to 1.689. 698, sorry. So then we've got third equation, especially move that there. Is everyone happy over here? Can you guys hear me still? Are you guys sleeping? Okay. Right, then what we have to do now is simply substitute all of this into equation 1. Yeah. So then what we're going to have is 1 times 10 to the power negative 3 equals stress AB now is B stress BC times 3,8197 times 0.6 divided by 200 plus BC we keep exactly the same, stress BC times 0.8 over 200 gigapascals. And now I have to substitute number 3, and number 3 was 1.698. Stress BC 1.698 times the length. So what I can tell you is that you can easily forget to put the length in. It's a very common mistake I see students make. They forget the length, the substitute, but they get the length. Oh, this is supposed to be 100 here, not 200. This is copper. Another mistake. Assuming it's the same material, but it's not. And that's over 200. Then now we can find BC on its own. The BC is a common factor. We can solve all of that mumbo jumbo. That'll give us something. I'll solve it now. Hope you guys get the same value. I'm not sure that is right. Let me just verify my answer. It's 3.8. Oh, sorry, I made a mistake. 8197. Now this is incorrect. You get 29, I think. 9491. Nope, that's also wrong. That's also wrong. I don't know what I'm doing here. You can just check my thing. I think someone's got it for me here. Who's got it for me? Yes, you can do a different way, definitely. You showed to me now. Many ways for this. So I'm looking for the value there. 3 comma. Just give me a second. You can do this using matrices as well. Times 0.4. Just making sure my stuff is right here. 22.856. It's a 6. Yes, there we go. And then there you should get 43.75218 megapascals. Are we happy with this? Brent, I'd like to hear your approach if you're happy.
So is this simultaneous equations can get a bit complicated sometimes. So
Yeah.
Can I take you back to your equation 1?
Okay.
That
Yes.
equation 1 can be rewritten as flea plus flea plus flea, right?
Yep, that's correct.
And then we have the length, we have what it
Same
takes.
force.
Yeah, we have the same force, which is common. We have the length, we have what it takes to calculate the area for everything, and we have the Young modulus. So we will take f out as a common factor, then we have f bracket, the remainder. We manipulate that formula, just manipulate that formula to make f the subject. Then we have f. And then you can just solve
force over area.
Yeah. You can just use force over area for each segment individually. Then you have one seemingly big calculation and a lot of small, simple calculations.
That's correct. We can definitely do that. Yeah, that's fine. That's perfectly fine. That's a lot better than this. Yeah. I'm just following the approach of the book. Yeah.
All right.
So yeah, it's the same. It's all the same essentially. Depends on what you're looking for.
Brent, just say that one more time, please.
I'll show it to you now.
Oh, okay.
So
Okay, so what do
what he's saying, so just I assume once you have BC, for us to find AB, you just have to substitute BC back into there and CD into there, right? It's simple, or BC back into to find CD. I hope you all get that. And then those values are going to be, I'll show Brent's for you now, 74.291 megapascal. And then AB will be 167.133 megapascals. So Brent saying the alternative is you go back to the first equation. I'm just gonna put over here. And because in a series arrangement, it's very easy to do. We use flee instead. So flee of AB plus flee of BC plus flee of CD. Because we're in a series arrangement, and of course, this is why we can do that, it's the same force acting here, right? So we take F out as a common factor, and then we have length E over A plus length E over A plus length E over A. Right? And of course, this is for AB, BC, and what's this? CD. So we quickly compute that. And of course, I'm just going to quickly throw it in here. 0.6. Just going to find everything. Brent, do you have that answer there? That what's in the bracket?
No, sir, sorry. It's difficult to write and follow everything that's going on, so I try to memorize.
Okay.
Sorry, man.
But you guys get the idea. I don't have to continue, right? So, and then you can find whatever there. You can find force, and you just find the individual stresses. Yeah. So you say force over area, then you should be okay. Does everyone know that? Does everyone act with the other approach? Hello. Yeah. So you can definitely, if you get the same answer, it's perfectly fine. There's no issue with me. Yeah. But it's convenient for series arrangement. Yeah, definitely. It's definitely convenient for series arrangement. You'll see the reason why I show you this approach, because when you go into like the other, like the parallel stuff, they kind of follow the same way of solving. Yeah. I mean, you could have even solved a 3x3 matrix with this. So, you know, you get that as well. Yeah, but for this arrangement, it's fine. All right. Do we have enough for today, or do you still want to continue? Who's ready to go? Do we have enough, or should I go? Yeah, we still have parallel arrangement. One parallel, please. Okay. So we do one more parallel one. You guys are on your way. Oh yes, I meant move on, not go. I meant like you do one more, and then but so I think you guys are fatigued here. See, with our brills ready to work. Okay, fantastic. Everyone else, we all happy? Tinama? Are we good? Albano?
Yeah, super good. So I think we can move
Fantastic.
on.
I like that. I like that. I like that. Okay, let's move on. Just give me a second. I was thinking, okay, no, it's fine. It's fine. I wanted to show you guys another way of doing this question. I'm not sure if you guys understood. It's using the matrices, but it's fine. Okay, let's just share again. I just want to be quick. Just one more, you said. And yeah. So now we're on a parallel arrangement, right? So in this case, guys, we have to apply new laws now. And if you remember for parallel arrangement, I said that the total force now is kind of the inverse of, okay, it's not obeying me. Just our forces are shared now, and then what happens now? Our forces are shared, and our change of length is exactly the same. So let's just get that right. Okay, just share again. Okay. Yeah. Okay, there we go. Yes, I will share the slides. Yes, I normally share once I'm complete with the lectures and stuff. You know, I think I have to change things. You're definitely entitled to the slides. Okay, I just want to get this, just zoom this up a bit. So again, so now we have a round bar, right? And it's placed concentrically in a copper tube. We put two, we fix it at the ends, and we apply a compressive load of 75 kilonewtons. Now, what I want to do, right, before we start, I want to ask you guys, what member do you think is going to fail here? Now, I'm going to say, I'm going to give you some values here, just along for steel and the copper. So I'm going to give you the allowable values, but I need to make a prediction. I'm going to see who's smart, who can figure it out. So which one do you think will fail? Just have a guess, you know, no pressure.
That's so. I think copper
Yes.
will fail.
Why? Copper will fail, no?
Yeah.
Okay, good. Why copper? Why copper? Because copper's weaker.
Because steel is stronger than, yeah.
Oh, fantastic. Okay. Anyone else? Who's got a prediction here? Mr. Silver, the PhD. Oh no, that's. Oh, now we have. Who's this guy now? Dr. Kiefer. Prof. What's your prediction? Quickly, guys. Just a small exercise.
I was once the cylinders are stronger than shafts, and the copper is a cylinder in this instance with a shaft inside it.
So which one will break? Or I don't know how you wanna. How should we spin it?
I'll
Which one will be
I'll say
okay?
the steel will break.
Okay. Why? Any
Because
reason
like I
why?
said, I was once told that cylinders are stronger than shafts.
Yeah. Okay. That's very interesting. That's very interesting.
Mm.
Okay. I'm just looking for a typical copper value. So just give me a second here. Copper yield. Can't actually find one. I don't know one off the cuff. It's small, eh? Okay, anyway, we'll get back to that. We'll get back to that. Okay, so now I have a new condition, and the change in length of steel must be equal to the change in length of copper, right? This is what's happening here. And then our total force is equal to, in this case, force of the steel plus force of the copper. So in this case, the total force is the shared amount of copper and the steel. And we've got a few hypotheses here. One says copper is going to break. Of course, it depends on the load, first of all. The load is able to break it, to induce enough stress to break it. And then we've heard that cylinders are stronger than shafts. Right. So let's see how we start this question. The first time we normally start this question, so we start on the total force, right? So it's exactly the same as before. It's 75 kilonewtons. That's going to equal stress steel, area steel, plus stress copper. Just call it ST over what's it? Area copper. So once again, you can see we're going to end up getting a what is this? We're going to get a setup where we have to put something in terms of something. So that's steel, and the area for steel. So if you're going to find this over here, it's going to be 1 over. You have to find the area there. It's force of the area, okay? It's exactly the same as before. So I think we get stress is not. This is whatever. This is correct for them. My bad. It's not saying. Stress times area, man. That's false. Sorry. Stress steel times the area. And the area for steel is going to be 490. So give me for that there. And then we have plus stress copper, and the area for copper is going to be 883. Now I probably should actually do this because some students are going to get confused, right? So remember, the first area is easy, right? So we have a round bar, so area 1. I'm just going to write the areas over here. This is what you should know, 0.025 squared. You get that area. To find area 2, because now you have a copper cylinder, you got to subtract areas, and it's going to be the outer diameter minus the inner diameter. Now the inner diameter is 30 mil. Right. So of course those will give you your 2 areas over here. So I hope that is clear to everyone. Straightforward. And then the next step, you have to go to change in length equation. Yes, the equation. And the change in length is going to be stress LE of steel. That's going to be equal stress L E over copper, and the lengths are the same, right? So we can ignore that. So stress steel over 200 GPa equals stress copper 100 9. Can someone mute their mic?
Okay, they say outside the meet.
Yes, can you hear? Hello? Your mics. Ivano, your mic, please. Almost unmuted. Okay. Oh man, what am I doing? Sorry. So once you have that, all you have to basically do now, simple enough, is substitute this guy into this. Brent, are you with me? So it's a simple thing. We substitute this into this, and then we can solve our stresses. So the other alternative way, which I like to do, because I like matrices, stress S, stress copper. I make myself a matrix, right? This equation now I have to rearrange like this. Hope you all follow me. So I'm saying stress steel minus 2 times stress copper. So stress steel for the first equation, and this is my second equation. So for the first equation, I've got 490.873 times 10 to the negative 6. Second equation, I don't have enough space here because it's so big. So you can either substitute or you can make a matrix, so I'm just showing you now. It's the same thing. Matrices is just a different way of solving it. When you have copper, this is now there and there. Copper is 885.573. Steel was 1. This guy is negative 2. This is equal to 75 over here, and that's equal to 0. So how do I solve a matrix? Because I rely too much on my calculator, I'll do that quickly. I'll show you guys now. So of course you could just done this by substitution. I'm just showing you an alternative way on how to solve this. That's cool. I hope I'm going to get the right answers here. Taking a calculated leap of faith. So can you guys see my calculator? It should pop up soon. And so all I'm doing now is I'm inputting my values now from the matrix. So that's the stress area, which it was. And the copper was 883.573. What is that again? Negative 6. That's equal to 75 kilonewtons. The guy was 2 from right. So steel was 1. That's negative 2. That was 0. And I'm expecting values of 40 and 80. Yep. I got the 80 for steel. And I've got the 40 odd for 40.368. I'm a bit off somewhere, but it's close enough. And I've got 40 odd megapascals for. I think I probably made a mistake with the units here. I wonder. Just have a look quickly. 49. That's fine. Oh, I wonder. Oh, 75. I made a mistake here. Sorry. There you go. Here's my right answer: 80.41 and 40.207. Are we happy with that? Or you could have just done substitution. It's entirely up to you. Same thing, just different ways. Students, see, that was quick. Are we happy with this? Okay, yeah, I'm just showing you the using matrices. That's all. So yeah, okay. We could just done a substitution, and now just back to the end of our lecture here. So I don't want to. Okay, so remember we posed a question just now, trying to figure out what's going to happen here. And if you look at, so we got stress values here. So one was copper and steel. They're both being compressed here. So steel was 80.414 megapascals. 414. And steel, sorry, and copper was 40. Push it off. That's 207. Now, if you look at my thing of us predicting which one will fail, what happens in this case is that steel takes twice the amount that copper takes. You see over there? And you can see it within the stress values. So and it depends on the material spec, obviously, right? So copper, depending which kind of copper this is now, I need to have a look at which, I'm not sure which alloy this is. I'm going to just choose a random alloy here. Doesn't really matter. Just give me a second. Okay, this is giving me in imperial units. Which I don't really want. Just if we just get an average, okay, we'll just say it's around 172, right? It's not that much anyway. Megapascals. So now let's just quickly see. So we have steel allowable and this, right? So again, we want to see which one's going to fail. Now in both cases, for this load, this is completely okay, right? But now, what happens if I increase this load to 500 kilonewtons, for instance? Let's say extra marks for the special students. Which will fail? Substantiate with a calculation. Okay. Can you guys perhaps find for me? So all we have to basically do is change this value here to 500 kilonewtons, right? And then see what you get. Guys, are you with me still, or am I going too far here? Have I lost you? Hello? Are we still here? Guess people are giving up. Welcome to Seconds and Chiefs.
We are here, sir.
So I've got a few questions. Are we happy with the parallel arrangement? Do we know how to solve for it? Is there any questions around that before I actually just add this? I guess it's Yes, Brent.
Hi, sir. So we
Yeah.
know that total force is force plus force.
Yes,
Can
that's
we
correct.
can we make that same statement about strain, where the total strain is the strain acting on the steel plus the strain acting on the
That is
copper?
correct. Yes, we can
Okay,
definitely do that as well. Yeah.
thank you.
Because it's the same length, that's why. So if you divide by the length, yeah, that's correct.
Okay, thank you.
Okay, cool. So are we happy with getting the stresses? I mean, there's nothing more than that really. Yes. Anyone else?
Sorry,
Okay, guys, yes.
sorry, I actually meant to ask this the stress, not strain.
No, not the stress. We can't do that. Yeah, that's not the stress. The strain is fine. Yeah, the changing length is fine, but not the stress.
It's a changing length of the same, but so we can't say the stress in the copper plus the strings,
No, it's not. Yeah, it's not.
Okay,
Yeah, it's
okay, thank
because
you.
it's the forces, and that's dependent on the area. So it's not as simple as that.
Okay, thank you.
Okay, guys. Let's. I think I'm gonna call it for today. People, I don't know if Tristan is tired. Mr. Silver's not saying anything. Um, I'll call it for today. I'll just look out for. I need to prepare a special tutorial, which will cover this work. Of course, textbook has a multitude, yeah, of examples. So make
Sorry,
sure you, yes,
all these examples that you're doing now in the slideshow is from the textbook.
that is correct.
Okay. So once I get the
Yeah,
textbook, then I can start doing these
yeah,
things nicely. Okay, cool.
great.
But when is
So
our
I'll
next
post.
strength class? Sorry.
It's next week, Monday.
Okay, I should have it. Thanks.
Yeah. Okay. So yeah, okay, guys. I hope you enjoyed today's lecture. Um, I'll see you next week for strengths. We got for the tutorial. And yeah, enjoy the rest of your day. Make sure you put in 3 to 4 hours of work every day, as I said you must. Yes. Thank you,
Yeah,
Mr. Yeah, yes,
so
Brent.
one last thing. You might not know the answer, but do you know if Mr. Levita is planning anything and actually having class today?
Yeah, I don't know the answer.
Okay,
I thought
thank you.
you could have asked me something else in strengths, but okay, it's fine.
I'm
Right.
just looking to the future. Yeah.
Yeah, no, for sure. So guys, hope you enjoyed it. Practice. Next week I'll start on shear and then straight into torsion. So make sure, and even tomorrow. So tomorrow is starting at 10 o'clock for electrodes, and we have 3 sessions. Is it 3? Yeah, 3 sessions, 45 minutes back to back. Of course, with breaks in between. I plan to finish up that chapter. But okay, guys, cheers, and see you again. Bye. Yes, Brent. Oh, Vano,
Sir,
who's